No, if you have guys, you should have a chant for the course of the meeting. I guess we could have it, but that's Inky Dinky. Why does everyone keep saying that? My feet are not that small. Was it fun? No, this is a 6.5. And they're a little bit big. Because when you my feet are not that small. That carbon that and everything that. Okay, well your foot, you have foam on the outside. This one at least you my feet are not that big. Yeah, and that's how exactly to 10, 11, 13, 42. I don't want to go to no, I don't want to see that again. Sorry.
Hi, everyone. Welcome to Lab 6. So this lab will go over the lab question on the midterm, and then we'll also do sort of a review of the differentiation and integration, solving for first order ODEs, but in the context of we'll calculate the errors of different methods. So question 2, we have a ODE here with some final condition instead of initial condition that is given. And we want to use forward Euler method. So if we think of forward Euler method, let's write out its equation. So f of x I plus 1 is equal to f of x of I plus f prime at x of I delta x. If you write down this is plus 3. And then it wants to have a negative step size and go back from 3 to 0. So that means we want to have, so f of 3 is given as 1. And we want to find f of 2. And f of 2 should be equal to the original value, which is f of 3, plus this at the same, but evaluate at the derivative. So f prime of 3 delta x. F of 3 is known as 1, and then f prime of 3 we can get from the ODE. So 2 times 3 times delta x, which is minus 1. So we have 1 minus 6 is minus 5. And then we can do another step. F of 1 is equal to f of 2 plus f prime of 2 delta x. And this is already calculated here. So minus 5 plus the derivative we find at original ODE. So 2 times 2 times negative 1. So that's minus 5 minus 4, which is minus 9. And f of 0 will be f of 1 plus f prime of 1 delta x is equal to, so here is minus 9 plus the original ODE is 2x, so 2 times 1 times delta x minus 1, which is equal to minus 9 minus 2 should be minus 11. So if you follow the formula, this should be what you get. Any questions? So 2 approaches. What we just did is for forward Euler to integrate backwards with a negative step size versus backward Euler to integrate forward with a positive step size. Are they different or the same? So no, they do not lead to the same result there are a lot of reasons. One of the reasons you can say forward Euler. So forward Euler is explicit, and then backward Euler is implicit. So they're different. You can also say we have this one is integrating backwards, and this one is integrating forwards, and one of the method will overestimate, and one method will underestimate. So you have to be vague. You can't say which one is over or underestimate because it depends on the function, the concavity of the function. So if you say that one overestimate and one underestimate, that's full credit. But if you assigned one to overestimation and one underestimation, that's incorrect. Any question on this? Okay. So this one. So it's integrating in the domain from 0 to 3 with a negative step size. So it doesn't raise an error, but it doesn't achieve the goal. The goal is this. So given this line of code, can you identify which line is incorrect? So this line 5, is incorrect. And how do we fix the problem? If we recall the arrange, this should be start, stop, and step size, step. And remind that stop is stop and not include X initial. So if you print this out in Python command, X will be equal to starting from 3 and then going to -1. So 2.9, 2.8, dot, 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 0.2, 0.1, and it ends. It doesn't contain a 0 because it stops, but not includes 0. So it doesn't achieve having 0 contained within the domain. So how we can fix that is X is equal to np.arrange from X final to X initial plus anything that's smaller than the step size, smaller or equal to the step size. You can say plus dx, comma dx, or you can say dx divided by 2. Or you can just write here instead minus 0.1. Anything works. Any question? So this question tests your understanding in lab 2, the basics of NumPy. D, you help your colleague to fix the problem. So upon expression of the variable x, the last element is this. So the expectation was that it should be around 0 because we're having the final point as 0. But this is giving us minus 2.6 times 10 to the negative 15. So this is correct and expected because this was what Python would output. This is correct and expected because this is an example of floating point error. Or if you mention anything about rounding off, the computer is discrete, you get full credit. And then this is testing your understanding on lab 1. Any questions? Okay. So here we have a forward Euler example, but here the code raises an index error. So the index error should remind you of something about for loop. So something is wrong here. So here we define the ODE, we define the list that we can store the results. And here we define the initial condition. So the forward Euler formula was that y of I plus 1 is equal to y of I plus y prime at I times delta x. So here is I plus 1, correct? Here is I, correct? Here is evaluating at I, so correct, correct, times dx, correct. So line 5 is correct. And because it raises an index error, there must be something wrong with the range. And I think in the lab before, we have encountered this type of error. When you are ranging to the x length, the x length should, if you range from x length and you get I plus 1, this will be out of range. So to fix it, we can say for I in range, x length minus 1. Remember to put the colon or else you'll get a syntax error. So here we should get minus 1 here. Any question? Okay. Is forward Euler's method an explicit or implicit method? It is an explicit method because if we look back to the equation here, everything on the right is already known. So this is known, this is known, this is known, and we do not need to do any root finding problem. So if it's implicit, you need to do root finding problem because on the right, we have something that's unknown, just like on the left. Any question? These should be lab 4. This is also lab 4. This is lab 4. This is lab 4 and lecture. Okay. Any questions on problem 2? Okay. And so today's lab will mostly be a review, but we'll also add something about error analysis. So we encounter many different methods, but why do we even bother looking at those different methods? It's because those different methods have different level of accuracy. But how do we quantify those? We can quantify the accuracy using errors. So we can first look at the simplest thing, the error at 1 point. We can define the absolute error as the numerical result you get minus the analytic result we get. That's the ground truth, the exact solution. And we take the absolute value because we usually only care about how big they are, not the direction. You can also define the relative error as the absolute error divided by the ground truth analytic result. So in the context of lab 3, numerical differentiation, when we get the derivatives, the absolute error will be the numerical derivative we get minus the ground truth derivative at a specific point. And same with the relative error. And we can code that up to look at the error of different methods. Okay, so here's an practice example. So here is everything from lab 3. And then we have a function, f is equal to lambda function of x of cosine of x. And we want to look at forward difference, backward difference, and central difference with a step size of these step size. So dx, we have a list of, so I can define it as 10 raised to the power of mp arrange, starting from 10 to the 0, 10 to -1, -2, -3. So -3, and then minus a step size. So we include the last one, -1. Okay, and it gives an error of value error. It says integer to the negative integer power are not allowed. So we can't raise an integer to something. So we'll make it a float. So now it gives what we want, 1 to 0.001. And then we'll need the for loop. So because we want to iterate on the dx. So for dx in dx list, we want to do something. And what do we want to do? We want to look at the numerical derivative of the function using these methods. So we have forward difference. So let's print the result. So print forward difference evaluated at what's the function? F. So here, F. And then the x, we want to evaluate x equals to 1. So we can define x point is 1. We'll define it here. So x point. And then dx. dx is here within the dx list. Okay, it says undefined because I haven't run this. So, okay. Now this prints the forward difference method at different dx. So I can format it properly with a f string. So f string means formatting string. You put any variable within the curly bracket. And I can say f prime of 1 is equal to this. And then because I'm enclosing a single quotation mark, I need to use an escape parameter. Okay, so you can also say dx is equal to dx, like that. Forward. And then similarly, we can do this for backward difference and central difference. So the key I use to copy this is on Mac is Option Shift down. If you do Option Shift down, it will copy the current line. And then you can do backward difference. So now it prints out the backward difference. Here's the forward and backward difference. And then again, we can do it for central difference. And we see that when the step size is large, they don't really agree with each other. When the step size is low, they really agree with each other, and that's expected. As the step size decreases, the error also decreases. But so we want to look at any question on this. So this is a review for lab 3. Okay, we want to look at how much the error is. So we want to calculate the absolute error for each method at each step size. And to do that, we want to first define what an absolute error is in Python. So let's define a function called absolute error. And it will take in 2 arguments, x1 and x2. So we'll just return the absolute value. So ABS is absolute value of the difference between those 2 numbers. So x1 minus x2. So if you try this out, if we have a number of 3 and the ground truth is 3.1, the absolute error should be 0.1. And this thing is expected because it's floating point error. Any questions? Okay, now we want to calculate for this function and list. We want to calculate the absolute error between each of those. So these should be x point. So we already know the forward difference method gives this result. This is forward difference. What about the analytic result? So the exact solution. So the analytic solution should be equal to, what's the derivative of cosine? It should be negative sign, and evaluate at x equals to 1. So the analytic result should be minus sine of 1. So we'll put that there. So minus NP sine of x point, as we already defined x point as 1. Okay, so we want to calculate the absolute error of this. So let's print this. Print the absolute error of forward difference compared with the analytic solution. Okay, we can keep this, print the dx. So these are the error, absolute error for the forward difference. And we can label those, so forward difference. Okay, and we can do the same thing with backward difference. So for backward difference, we want to get the absolute error between the backward difference method with the analytic solution. Same thing with the central method, central difference method. So we see that as when we have a large step size, the error is relatively large. But when the step size is very small, the absolute error also decreases. So I think it lets us to plot the result. So we have given here the for loop, but we want to plot the result. So how do we plot this? So we can plot, so for plotting, we can have a fig x is equal to plt.subplots. So we have an axis, and then in the axis, we can plot with this for loop. So in order to plot it, we want to record the result. And how do we record the result? We can use a list. So we have the absolute error of forward method list, making it empty initially. And then do the same thing for backward difference. And then the central difference. So they are now empty. But we can append the list. That is, append meaning we add to the end of the list. So we can, within this absolute error of forward, append the result of the absolute error here. So we copy that. So if we run this, if we look at the absolute error forward list again, we have the results being within the list. One common error for this is that if you run this again, it will add to the list again. So you want to define the empty list every time. So I would put it in the same cell. So every time you run it, it's still 4 items. Okay. And then we'll do the same thing for backward difference and central difference. So I copied that. So here should be a backward difference. Then change the variable name for. So if you want to change these at the same time on a Mac, you can press down Command. So you have 2 cursors available at the same time. I think on Windows, it's Control. So you can control these 2 cursors at the same time. So central difference. Okay. And then with this list, we can do some plotting. So we can plot the absolute error of forward difference method with respect to the X list. Okay, that's a line. And let's make it a point with dashed line and then label it as forward. We see that because we're taking the dx on a logarithmic scale, you see that this is like not a great representation because everything will be at the very bottom here. So what we can do is to make this a log scale. So currently it's linear on x and linear on y. What we can do is to make x and y axes both logarithmic scale. And the command for that is log. So here we have changed the x and y to log. So if we want to do only one axis, we can do semi-log x. So that will change x-axis to log. And then semi-log y changes the y-axis to log. And for both, it's log. And then we can do the same thing for backward difference and the central difference. Okay, we still don't know which are those, so we can get a legend. So the forward is blue, backward is orange, central is green. And then let's label the axes, set x label as dx, and set the y label as the absolute error. So what do we observe here? As dx decreases, the absolute error for all the methods also decrease. The forward and backward methods errors are very similar to each other, but the central methods difference, the central difference methods error, it's much lower than forward and backward difference. So that means that the central difference method has far better performance than forward and backward difference. Okay, what step size gave the best result? So the lowest step size gave the best result. And what method gives the best result compared to analytic result? So the lower the error, the better it compares with analytic result. So central difference method has the best result. Any questions? And then you can practice this with another function and various step size. And we'll come back in 15 minutes. So that's right. So you look at the error. It says integer to the negative initial power is null. You need to make it a float. So 10 needs to be a float.
Oh, so it doesn't think of that as one. Thank you.
Okay, how are we doing? So for this practice problem, define the f function as lambda of x, numpy tangent of x plus x squared minus exp 0.5 times x. And for ground truth, what is the derivative of this? The derivative of tangent is secant square of x. And what is secant? Secant function should be 1 over cosine. So secant of x is 1 over cosine, and secant square should be 1 over cosine square. So np dot cosine x squared. Derivative of x squared should be 2 times x. And derivative of e raised to the power should be chain rule, so 0.5 times np exp 0.5 times x. Okay. And we want to evaluate at the point of x point of 1.5 using 4 backward central difference methods with step size of the x list is equal to 10.0 raised to the power of from minus 17 to 0, and then minus the step size, which is going positive, so plus 1. And then we can verify that it's from minus 17th to 1. And then we want to calculate the numerical derivative for the function. So for each dx in dx list, we want to print the result. So let's first print dx is equal to some dx to verify this. Okay. Then we can print the result. So for forward difference, we have the forward difference function. And then evaluate it for the function, the x point, and the dx. And the dx is here, being iterated. Dx. So here we calculated the derivative for a different step size. So interesting to see that at very, very small step size, we get wrong result of 0. And then when we have intermediate step size, it's correct. And when the step size is too big, of course, it's wrong again. And we'll see why in a second. And we can do the same for backward difference. And central difference. And it's consistent between different methods. Okay, and part B, we want to calculate the absolute error. So we'll reuse, I'll just overwrite this and then reuse this part. So we want to find the absolute error for forward difference and create an empty list to store it, and do the same thing for backward difference and central difference. And I'll put all these empty lists right before the for loop so that we don't have any error. And then for the forward list, I will append to it the absolute error between the forward difference versus the analytic result. And the analytic result will define within the loop, which should be the derivative. So f prime evaluated at the x point of 1.5. Okay, let's try that. And then print this. Yeah, so we have different numbers here representing the absolute error for forward difference method. Can do the same thing for backward and central difference. So change this to backward difference. And then change this to central difference. And we can plot the result. So big X is equal to PLT dot subplots. And then on the axes, we'll plot the absolute error of forward difference method with respect to the X list. Then make this point with dashed lines and then label this as forward. And then because this is on a linear axis, we should change this to a log. So here's the behavior when the x and y are on logarithmic scale. I'll repeat this for backward difference and the central difference. And then I'll put a legend, and then label the axes. Set x label as dx and set y label as absolute error. Okay, what do we observe here? So we see that there's a kind of a minimum in the middle. The absolute error reaches a minimum. So when the step size is really large, the absolute error is very large, as expected. As we decrease the step size, the absolute error decreases. But to a certain point, it rises up again. The reason is because on the right side, the dominant error is the error associated with the numerical method. So the forward difference, backward difference, and the central difference. Those are the error associated with the method. But when the step size is very small, there's another type of error that we introduced in lab 1, which is the floating point error or the round-off error. The floating point error scales differently. It scales with 1 over dx. So as when dx is really small, the floating point error is really large. So there's a trade-off between the absolute error and the error associated with a numerical method. So this shows us that it's not that the lowest step size gave us the best error. It's that there's an intermediate sweet spot instead. There's a trade-off between the two errors. And if you want to dig deep into the derivation, there's a YouTube video I would recommend watching. Any questions? Okay. So far we have looked at the error at one particular point. But usually when we use numerical methods, we're evaluating it along an entire domain. So within the domain, it has a lot of different points. So how can we quantify the error within the whole range? So different approaches, there are approach called the sum of squared error. You first take the absolute error and square them, and you sum the squared error. And that's called the SSE, or sum of squared error. Because the squaring term, it penalizes the outlier, so it's not very robust to outliers. We can also define a mean square error. So we take the square of the absolute error and then find the mean. So these two types of errors are squared errors. So their unit will be the quantity squared. So we can't directly compare these type of error with the quantity we're measuring. But we can also take the root of the mean squared error. So we take the root of MSE, and now we have returned to the original unit. So we can compare RMSE with the original quantity, but not SSE and MSE. Any questions? So let's do an example. So first, again, we calculate a numerical derivative. Now, differently, we have a range instead of a point. So we have x minimum is -10, x maximum is 10. And then the dx, we have a list of dx. So dx list is equal to 10.0 raised to the power of, this is 10 to the 0, 10 to the -1, -2, -3. And then minus step size, which is plus a step size, which is -1. And the step size is -1. You can verify this from 1 to 0.001. And we have our function is, again, cosine of x. And then the x point we want to evaluate, oh, it's within the whole range. So we don't have a point, we have a range. Okay. And we want to evaluate the derivative using these methods. So for dx in dx list, we want to print dx is equal to dx. And then we want to print out the first 10 points of the forward difference. So forward difference method evaluated at f, which is the cosine of x. And then x, here we have a list of x. So list of x should be ranging from a range from x minimum to x maximum plus the dx, comma dx. But the dx is only defined in the for loop, so we'll make the x within the for loop. X, and then evaluate at dx. So here is also dx. So these are the first, all the points. But we only wanted the first 10 points. So we should do a list slicing. So colon 10. That's the first 10 points. And then we can do the same thing for backward and central difference. Okay, any question? Should again be a review of lab 3. Okay, now we want to calculate the different cumulative error for this method at all step sizes. So let's first define these functions. How do we define those? So the sum of square error, or SSE, we again take in two values, x1 and x2. What do we return? We first find the absolute error between them, so x1 minus x2, and then we square them. So there's a square term, so raised to the power of 2. Then we add them up. So we'll do a sum. Okay. And for the mean square error, MSE, again, we're taking x1 and x2, and we return, again, it's the x1 minus x2, and then we square them. So this is the squared error. And then we take the mean between them. And to take the mean, we can do dot mean. And then the root mean square error is RMSE, taking 2 points again. And then this is the square root of MSE. So I can just copy the MSE here and then do the square root. Or alternatively, you can also do return the square root of the MSE between x1 and x2. These are equivalent. So I'll copy this down to our problem. So now within the for loop, we want to store the different values of the errors. So we have SSE for forward, list is empty, and then do the same for backward and central. And then not only SSE, but we also want MSE and RMSE. So we change these to MSE and RMSE. So we have defined the empty list to store the values. And then within the list, we want to calculate the error. So we want to append the value. So SSE forward will be the SSE of the forward difference here, this whole thing, compared to the analytics result. And the analytic solution should be the derivative of cosine should be minus sine. So that will be minus sine NP of sine evaluated at the different x's defined within the for loop. Okay, you can try this out. So x min is not defined. So I think it should be x dash. Okay, that works. So that the SSE of forward has 4 components. And as the step size decreases, the cumulative error also decreases. So we can do the same thing for backward difference. and the central difference. And here we only calculated for SSE, so we want to change it also for MSE and then RMSE. So we'll select all these, should be MSE. And then the same thing for here, RMSE. So here we have calculated everything. And then we want to plot those. Since we have 3 different types of error, we want 3 different subplots. So fig x is equal to PLP dot subplots 1, 3. And then let's change the figure size so it's less crowded. So there are different axes. So for the first axis of index 0, we want to plot a log-log plot of SSE forward with respect to the x-list. Let's make it a dot dash, and then also give it a label forward. Okay, do the same thing for the backward difference and the central difference. And similarly, we do it for MSE and RMSE. So we change this to the second plot with index 1. And this is MSE. Then again for RMSE, the third plot with index 2. Okay. And then we want to label these. So the X label are the same. So I can just do it for I in range of the 3 plots. I want to label the plots with X label of the X. So now it appears here. But differently, the y-axis is different for each individual one. So axis of 0 set the y label as SSE. Do the same thing for 1 and 2. So 1 is MSE, and then 2 is RMSE. And then because we have multiple plots, we can do the height layout command to avoid crowding. And then we still don't know what the colors are. So we can, for the last plot, because they all share the same legend, so we can just do it for the last plot. Give it a legend. Okay. So here we have the final result. We see that we only see the orange and the green line, but we don't see the forward. That's because the forward line is actually under one of these lines. So let's change the forward one to a solid line. And then see that. So we see barely there's a blue line down there. Or maybe I should just delete the dot for the backward method and give the dots here. Oops. Should be an O. Okay, now you see that the blue line is actually under the orange line. So that suggests the forward and the backward method has same error dependency, but the central method has far better performance, meaning that as dx decreases, the summed error are always smaller than forward and backward difference. Any question? And because, again, SSE and MSE are squared errors, they cannot be compared directly with the original value. So we can compare it to the machine precision of 10 to the negative 16, but RMSE can be compared. The subset that gave the best result with the current data is the smallest, 10 to the negative 3. And the best result is given by central method with the smallest summed errors. And you can practice this with a practice problem. We'll come back in 15 minutes. Are we done with this? Are we done?
There are a bunch of errors.
Okay. You need help?
So what does that mean? Like two different shapes, like where it's at? Like this is a different one. The worst. Okay, this is supposed to be X max, X min.
But this is good. So maybe causing the issue is that see that causing the error because the reason is that it's recognizing this plus this minus this but first 10. So you use big and close the whole thing. The whole thing. No, the function.
Oh, the function. It's not supposed to be a function. Okay.
Because it's original without the it's recognizing this thing, you take the first numbers.
Yeah.
This has 2000, and 10.
Oh.
So what now we're doing that is that let's calculate these first.
And then
Okay.
okay, now
Yeah.
I'm gonna ruin your agenda. Getting number one. Yeah. I think number one. I think number one is one that was really how do you even do this? This thing? Oh. Remember this thing? How do you do that? What is so he's just doing the whole thing. So when we text it, is that not at the channel? If we don't go at channel? Like, do you see this? Is it Jones? So he wanted to see special. That's totally it. Who's that? Who's that?
Okay, I'll quickly go over the practice problem. Basically, you can do what we just did to code from scratch, or you can copy and paste from the practice problem. So we have the forward, backward, and central difference, but this time the domain we want to change to -1 to 1. So -1 to 1. And the function instead of cosine of x is tangent of x plus x squared plus exp 0.5 times x. And the dx list becomes from -7 to -1. So -7 to -1. And then this is +1, so minus +1. And then we can verify that the x list is from 10 to the -7 to 10 to the -1. Okay, and then for the printing of the derivatives, the f corresponds to new function. X is the new x here is the x minimum to x maximum plus dx. Okay, and these are the derivatives. It will take some time. And you see that it takes much more time for the ones with small step size compared to large step size because it has more calculation to do. Now we can do the plotting. We first define the empty list. Now we define the SSE, MSE, and RMSE. And then we do the calculation. And we check that X, these are all defined. The analytic solution now is secant square of X, so 1 over the cosine of X squared plus 2 times X plus 0.5 times NPEXP, 0.5 times X. And then forward difference, backward, central, SSE, MSE, and RMSE. So we run this, we have calculated them. And then we can do the plotting. Let's see, do we have to change anything? So the range we might need to change. Let's see what range. The range is from -16 to 2. -16 to 2. Okay. So let's plot it. And we see that again, the backward difference and forward difference have same error profile, but the central difference has much better performance. So it doesn't just decrease forever, it does increase because of the floating point error trade-off. Any questions?
You go back to the
Analytic solution here. So this is secant square of x, derivative of tangent. This is derivative of x squared. And then this is derivative of e to the 0.5x with chain rule. We don't have a secant function in Python, so we have to use the trig identity. Okay, and so why do we observe that forward and backward difference have the same error but not central difference? We can do analysis with Taylor series expansion. If we expand f of x plus dx and x of minus dx, here are the terms. And from the definition of forward difference, we have f of x plus dx. And if we substitute this inside here, and then minus f of x, so f of x here cancels out, and we have everything later here, and then divided by delta x. So we get this. If we compare the left and right hand side, we see that y f prime is the same. So everything else here is error. We see that the highest order of error is with respect to delta x. Because we want delta x to be smaller and smaller, so the lowest order of it is the dominant term. So it's order of delta x. So the big O notation here, the O here denotes that the order of the error is proportional to delta x. So as we make delta x smaller, the error also decreases. And if we decrease the delta x by 10, the error also decreases by 10. So it's a first order method. Similarly, we can do it for backward difference. Now we're substituting f of x minus dx. And after substituting, we see this term. Compare left and right, we see everything else here is error. And the leading order error term is delta x. So again, it's a first order method. When we decrease this by 10, step size by 10, the error also decreased by 10. So because forward and backward difference are all first order method, of course their error overlaps with respect to step size. The central difference method uses both x plus dx and x minus dx. So if we substitute all these things in and then do some calculation, which is the practice problem 3, you need to derive it. We see that the highest order error term is delta x squared. So this is a second order method. So it means that if I decrease delta x by 10, the error decreases by 10 squared. So it decreases by 100. And you can try the poll everywhere survey. For backward difference method, if I make the step size 1/5 before, how much will the error be? So the backward difference is a first order method. So how much I decrease the step size is how much I will decrease the error. So the step size is 1/5 before, the error will be 1/5 before. For central difference method, it's a second order method. So if I decrease it by 1/10 before, the error will be 1/10 squared. So it will be 1 divided by 100. And then this you can show it with pen and pencil. You just substitute these two into the definition of central difference method, and you should arrive at this line. So far we have been looking at error in the context of numerical differentiation, so taking derivatives. But what about numerical methods for solving ODEs? So as an example, the forward Euler's method, if we write the Taylor series expansion of x plus dx, we get everything here. The first term is exactly the forward Euler's method, f of x plus f prime of x times delta x. 1 factorial is just 1. So everything else is error. And the leading order error term is order of delta x squared. So this is the local error for the forward difference method because it's the error associated for each time step. And because we're integrating with the forward Euler's method, every time we go through a step, we multiply by delta x. So the delta x cancels out with the delta x squared. So that the global error for forward difference method is order of delta x. So it's a global first order method, a local second order method. And because we usually communicate only the global error of numerical methods, the forward Euler's method is a first order method. And in general, if we have a numerical method with n order local method, the global method should be n minus 1. So here the local is 2, the global should be 2 minus 1 is 1, so first order. With some similar analysis, I'll just give out the conclusion that backward Euler is also a first order method with global error of delta x. Midpoint method is a second order method, so it's better than forward and backward Euler with global error of delta x squared. RK4, by its name, it's a fourth order method with a global error of order of delta x to the fourth. So we look at these problems. For forward Euler's method, which is a first order method, if I make the step size 1/10 before, the global error should also decrease by 1/10 because it's a first order method. For RK4 method, if I make the step size 1/10 before, because it's a fourth order method, the global error should be 1/10 raised to the power of 4. So 1 divided by 10 to the fourth. So 1 over 10,000. For midpoint method, if I make the step size 1/10 before, the number of steps needed to cover the same domain is how much? So because we have the same domain, but I make the step size smaller, we'll need to take more points to compensate for that. So the number of steps needed to calculate with the same domain should be the inverse of this step size change. So 1 over 1/10. So it should be 10 times more. Makes sense because if we make the step size smaller, we still have the same domain. We'll need to do more steps. So that's why if you decrease the step size, the time for the calculation will increase because you need more steps to get to the same endpoint. So if I set the step size to 10 to the negative 17th, you'll get 10 to the 17th more steps you need to take. The global error of a method that's 6th order local error, what's the global error? So the global error is the local error's order -1. So it should be 5th order global error. And then the practice problem here is in the context of solving first order ODEs. And you'll use the similar concepts in the numerical differentiation. You will calculate using backward, forward, and midpoint and RK4 and SciPy integrate and compare with the analytic solution. Okay, so that's all the instruction for this lab. We still have 20 minutes. You can stay here for questions, or I don't have anything else. I'll stay here till 2.
We're gonna bring down 6, so he's gonna want that stuff. Because we're gonna like in 5 6. I'm corporate things. Or only mega thing mega you're nice. So all these and maybe also his corporate his people. Rice makes the world go round. This stuff like literally have to come. You should have seen mine from my math class because he made us print out all. Oh yeah, we ordered. How do we get it? Where did you get it? Costco? I didn't go to a Walmart and go to a and I was get it. And that's also when I first saw people leaving. And I freaked out. It's not that bad. I'm not doing something. The gas costs more than the CVS. CVS. Is there a printer store? You just ordered it. Oh, this is my phone.
What is it like?
But it says it to me. Wait, how do you find that here?
I don't see that. It's the song.
Oh, there's Slack official ones. Oh, it's so cute. Wait, I'm gonna send another one. Hold on, look at this. Look at this. This pickle one. Look at this pickle one. I like this one. Wow. I think. There's an accident. Where? Where? Oh my god, they made a sticker. Wow. We joined the AQ. The IP. It should be said with American. But I like institute, so it's like American, you know. AP sounds better than IP. Like it's just like it's the American Institute company. It's just like someone else. It wasn't hard because it sounds very fancy. Yeah, that's they're like, yeah, we're like our recruiting, you know. We make them over. Yeah. Dude, we didn't get everyone to go. It would just be like 3 people. Yeah. Including.
It's very clear. I regret
How big is that? How big is that?
Because I got it from out. And then, so therefore this one.
Including the chairs?
Yeah.
Oh,
So there's 2 chairs.
yeah,
So kind of
the same.
the same. Except they all want to just maybe one friend.
Yeah.
Also, I think it's a little bit friend.
That's so funny.
Yeah.
And ink. Do they sell ink at Trader Joe's?
I was gonna go to the.
I do.
This is like survival. You probably just would it, right?
It isn't. No, she's really right. I saw that.
She's really right.
I remember seeing it.
After this.
Guys, it's been a year since I bought my headphones. And then you're like, oh, these are nice. Wait, what kind of desk get? Do I should say black? Two 700. That's
What are you talking about?
67 black ink cartridges. How much did you pay for this? $17.
Yeah, it's the 67.
Oh, I can see it too. Oh my god, I'm not clicking on it.
Oh, I just, let's see if we're on this fucking friends.
Selling three.
Is that like, you nodded and you forgave you? I'm gonna. It's like.
Dan texted me the other day, he's like, do you want to sell? I was like, not really, but like, what did you need? And he's like, oh, I have these two like big holes in my Seahawks shirt and I really want to go like watch the game in my shirt. It's on Thursday, please help me. And I'm like, I was like, dude, the 7K, no. And I was like, and you're like, what? And I was so kid, and I'm like, I can give you one, like I have a mini one that I stole from a hotel. He was like, oh, okay. And then he like texted me and he's like, it's okay, actually, I'm gonna go home this weekend and I'm gonna go to a real game. I know.
I could read one of the
You really want to get that. The only thing you can
I thought maybe I was double check this one. Thank you.
This was just
Yeah, like close and then
That must be. So the minus.
Some of the stuff, yeah, even if it's negative. There's a
So the exponent doesn't.
Like I think my
So if the instructions.
In the previous process, right? Like my.
I'm getting parent, but it's not like.
So do you want to be needs to be one? Needs to be like instead of one. So currently it's so
So what is the so like reliable that the third one was made.
so
But it's still actually makes on the bottom down.
so in this case it should be E and so accent. So it should depend on independently, but in this case it doesn't. But the general form is accent. You can give Y as nothing or anything. It doesn't change the. But the standard is to
So it's kind of
yes. So meaning that whatever you put as one doesn't become and at 0 at the 10 they're in the zone. It doesn't. It's just for some points. Because if I just do this, it will work for these, but for time second, you need to rewrite. Because second recognize the function is dependent independent object.
No, because it's not hybrid. What are you going
So these three arguments, the other results, invariably means
I don't know why. The reduction of human circle.
to infer that he's been function. Line.
Yeah. B. Yeah. But it's definitely not.
You can just use that.
Yes. No, because that's yes. You know how you do the values? You know when a little what's your actually
Oh, also have one that is nothing about really easy because that keeps the outcome. So but sci-fi optimizes points here into so
all but the graduate work on
what you're thinking is that LDS is so which should have been output
No, probably because you need to start in the break. You want to say minus another. So you want start at that. No,
So like,
That's how.
C-SPAN is your, I guess your end and your start and final, but like it's you, I was like the middle.
Yeah.
Yeah, so this is another floating. Because it's not the first one, that's exactly so
Okay, three vectors, which will use one.
it's index zero. It's the first one.
You really need to want to start out number.
Y zero is also this, even if you only have initial.
Like that, and what does it mean, like center effects, like having a function, like so
No, you don't.
so that in this case, the sub, the orientation of the substitution. Even if these class lines,
That's more for where concern of limits. Setting the ratings of sentence.
allows.
Whatever is at the forward. Well, actually, we like Y zero to be a number for each. That's like there. The reason that you want some bracket is in cycle is because you want it can solve systems of the limits. And if you have system, you have code. So why that's why. It is a different. That's not that solution for see, it's a different one. We need to get first one. The end of second.
Yeah.
Down to regular. Let's say one. And then we can see the first one.
I have this journal form. We're gonna look at why I was looking at where.
But because the solution. And they will be one, so without one, the students find out one.
Oh.
This will be not terrible in